All right, let's go ahead and start with our next chapter, and that is going to be chapter 6. And in this chapter, we're going to focus on something called the normal distribution. You might have heard of this at some point in your life. You probably don't know what it is or what it's used for, but out of all the distributions that we've covered, whether it be binomial, Poisson, geometric, all these different probability distributions. This one is by far the most important. It's also probably one of the most important things that we'll talk about in stats this year. So first thing I want you to do is actually do a little research. I want you to determine what is the normal distribution and also what does it look like. So what is it? What does it look like? Take a minute to do that on the internet or your textbook. All right, hopefully you came up with some good answers for that. One description of the normal distribution is that it is a veritable Boy Scout knife of statistics. What does that mean? Well, Boy Scout knives are used for a lot of things. They have a knife, they might have a little screwdriver, they might have a toothpick, they might have some tweezers, a little pair of scissors, a little corkscrew. So they can be used for a lot of different things, right? A lot of uses, very handy to have. Normal distribution can kind of be thought of in the same way for statistics. It's used in a lot of different areas and applies to many different things in statistics. This normal distribution can also be referred to as the bell curve. You might have found that at some point in there. The bell curve also could be called the Gaussian curve. Bell curve is probably what you've heard of at some point in your life. So it follows the bell curve. It's a bell curve shaped. Well, that's the normal distribution. It was studied extensively by these two guys. First one being Carl Friedrich Gauss, hence the name Gaussian curve. And also this guy, Abraham de Moivre. So two famous mathematicians that really did a lot of work with the normal distribution, kind of brought it to the mainstream and applied it to statistics. Some things you need to know about the normal curve. It is smooth, meaning that there's no sharp edges, right? It's a nice smooth curve. Also, the center of it is a vertical line, and that vertical line is at the mean there. So if you were to draw a vertical line straight up the middle of this, it would be smooth. That would be the mean. And also, it's symmetric as well. Symmetric meaning both sides would be equal. So it turns out that there's actually 50% of the data in this side, and there's 50% in this side. And we'll talk about that more in a couple minutes. But it is symmetric, so one side is an exact mirror of the other side. This curve approaches the horizontal axis, gets infinitely close to it, but never crosses it. Never ever crosses it. If you're familiar with the term an asymptote from Algebra 2, it's like an asymptote kind of there. It never crosses that line, so that should be there. It gets infinitely close to the axis, but it never actually crosses it. The highest point up here is always going to be the mean. So that's the mean, right? Extend straight down. And the total area under this curve is always 1. Area equals 1. You can also think of that as 100%. So 100% of the data lies inside of that curve. So the area would be 1 if you were to look at it as a decimal. So area is always 1 or 100%. All of the data lies under the curve. A couple other things about the shape. If there's a large standard deviation, meaning that is more spread out, it's going to look wider. So it's sort of wider in this case. If there's a small standard deviation, meaning that that is sort of more scrunched together, it's going to have a higher peak. So it's going to be skinnier. So here's just a couple different examples here. If we had a mean of 100, you can see all of these, their peak is at 100, right? The pink one there has a variance of 9, though, so it's a very steep peak there. The green one has a variance of 36, so it's a little bit wider. And then the purple one has a variance of 100, so it is even more wide. All right, so when is this used? When is the normal curve used? Turns out most things in life are modeled with the normal curve. This is an example of IQ scores. So the average IQ score is about 100, be right there, the mean. And then if you were to sort of extend this out, the empirical rule, which we'll talk about more in just a second, states that if you look at this first section here, 68%. So you can see the 68 here. So 68% of the population, I'm going to write this out, 68% of population lies in this interval here from 85 to 115. That is one standard deviation of the mean. So we could say 68% of the population has an IQ between 85 and 115. Okay. If you extend this out a little bit further and you extend it out here to include the 70 from 70 up to 130, that's actually two standard deviations of the mean. So adding 2 and subtracting 2. That states that approximately 95% is going to be in that interval. So we'll talk about more of that in a little bit more in just a minute. But every major thing, like whether it be age or weight or height, lots of things we'll talk about follow this normal distribution, and we can use these facts, the empirical rule, to make determinations about the population. So another example here, somebody did a study on the heights of adult English male criminals in the year 1900 or so, and they plotted them, and it turns out they actually fit the normal curve. So if you were to look at this curve here in the 1900s, the average height for a English male criminal was just under 5.5 feet. So you can see here the mean was 5.456 feet. So about, close to about 5'5", 5'6" was the average height of an adult English male criminal. And you can see as you extend out here, very few were at 6 foot. Also, not really anybody there down there at 4.5 feet. But anything that you look at sort of as height or weight is generally going to follow this normal curve, meaning that if you have the mean, there's going to be an equal amount on each side. So essentially what this is saying is there's an equal amount of criminals, taller and shorter than 5.456 feet. So because it's symmetric, right? So if the mean is 5.456, there's going to be an equal amount of criminals taller than that and shorter than that, which most of them will fit sort of right around that range of about 5'6" or so. Another example is U.S. This is birth weights of newborn babies. So this was a study done in 2002. They looked at the weight of 3,226 newborn babies. You graph them out, they actually followed the normal distribution as well. So the average weight, 3.39 kilograms. And as you extend that out, follows the normal curve as well. And last one I want to look at here, U.S. female heights. So the average height for a U.S. female seems a bit high, but this says 5'8". So that would be the average height. And then with this, using the empirical rule, which we're going to be talking about more in just a sec, you could say approximately 50% of females are taller than 5'8", right? And approximately 50% are less than 5'8". And let's say you're really tall, right? Maybe you're 6 foot. Okay, so you're 6 foot tall. And you want to know, like, what percent of the population of U.S. females are you in? Are you in like the top 5% or the top 10% or top 20%? Well, using this empirical rule, we can see everyone 5 foot and higher, 5'11", and higher, compose 2.35% of the population. So if you're above 5'11", you're actually in the top 2.3% of the population in terms of heights of U.S. females. If you're somewhere between 5'6.5" and 5'9.5", you're kind of right in the middle there. You're in the middle 68% of the population. If you're below 5'6" or so, then you're about the bottom 15% of the population. So you can see how this would be useful. Some facts about the empirical rule, which is going to be what we focus on for this particular assignment. We can say that approximately 68% of the data lie within one standard deviation of the mean. So you're going to want to write this out. It's also true that approximately 95% of the data lie within two standard deviations of the mean. Not sure why that's crooked. And then our third fact here, using the empirical rule, is that approximately 99.7% of the data lie within three standard deviations of the mean. You don't need to worry about how we came up with that at this point, but these are facts that are true and we are going to be using to solve the problems that we're going to be doing. So definitely write this down, pause the video if you need to. All right, so here's a graphical illustration of kind of what we just said. So this is the empirical rule. If we got the mean in the middle here, and we were to add a standard deviation and subtract one standard deviation. Well, within that interval, 68% of the data would lie within plus and minus one standard deviation of the mean. If we were to add two standard deviations out to here and subtract two standard deviations out to here, we could say that 95% of the data is within between these two standard deviations. And if we were to go out one further, to three standard deviations of the mean in both directions, then we could say 99.7% of the data lie within three standard deviations of the mean. So this table here, very important. So with this empirical rule, we can actually further divide this. So I'm going to just draw a little illustration. Draw a little normal curve here. All right, and if I put the mean in the middle, let's call this mu, you're going to be drawing some of these charts. So it is a good idea to copy this down. And then let's just draw one here. Obviously, it's not 100% straight. All right, so if the mean is in the middle there, I'm going to go ahead and just draw another line here. Actually, let me switch colors. So I'm going to draw a line on both sides here. Try to make it about even here and here. So this red line represents mu plus one standard deviation. So the mean plus one standard deviation, or mu plus sigma. And then on the left side here, this would be mu minus sigma. So that would be one standard deviation of the mean less than it. Right. So we said in the previous slides that 68% lies in there, right? 68% lies within plus or minus one standard deviation of the mean. Which also means, since this is symmetric, that 34% of the data lies in this part here, from the right side of the mean to the first standard deviation, right? And then another 34% lies in this part right here, because we can divide that in half. So if there's 68 in all of it, well, there's 34% in each part of it, right? Okay, now if I were to extend this out a little bit further, and let's say two standard deviations of the mean, so mu plus 2 sigma and mu minus 2 sigma. Well, within this here, or to sort of scribble this around, if we look back, within two standard deviations of the mean, we said that 95% of the data lies within two standard deviations of the mean, right? So 95% there, which means a couple things, right? If we were to divide that directly in half, we could say that 47.5, because we're divide that in half. So there's 47.5 in this half, right? From here to here, there's 47.5%. And then from here to here, there's the other 47.5%. Right? Because each of those could sort of be divided in half. Another thing that's important to note is that if it's 47% from here to here, right? And it's 34 from here to here, so this is 34%. And then it's 47 up to there, we could say there's actually 13.5% in this little quadrant right here. So 13.5% of the data would lie in that little section right there, which also means 13.5% would lie in this little section right here, because that'd be the difference from 47.5 minus our 34%. So hopefully that makes sense to you where I'm coming up with that. Okay, and if I were to go one more out, we'll be applying this in just a second. So if you're still a little confused, just hang on there. If I were to go out to here, mu plus 3 sigma and mu minus 3 sigma, well, we said that 99.7% of the data lies within 3 standard deviations of the mean. So if I were to extend this around, 99.7% fits in there, which means each half from the middle out to there, we take half of that, half of 99.7, well, that would be, you do the math there, take a second, 49.85%, I believe. Better check my work there, hang on. Yeah, 49.85% would be in that half, right? And there would be 49.8% in this half. Okay, so hopefully you're still hanging with me there. All right, now if I want to know how much is in this little section here then, in this little section here, well, what I would do is 49.85 minus my previous one, which was 47.5. So that tells me approximately 2.35% is in this little section, which means 2.35% is in this section as well. Right. And then if I wanted to take this one step further, figure out how much is in the remaining portion there. So whatever's left, let's go blue. So whatever's left in this little tip here, the percentage in that little tip. So that would be greater than 3 standard deviations and less than 3 standard deviations. Well, there was a total of 50 in the whole side, right? So the whole side is 50. And we used that 49.85. So that tells me there's approximately 0.15% left in this one. And then approximately 0.15% left in this. Sorry, not 0.15. Yeah, sorry, 1.15. Sorry. All right. So this is actually an important chart. You might want to write down this as well. You don't need to do all the scribbles at the top, but write down how much is in each one of these sections, because when we do these problems, you might be adding some of these sections together. For example, if the question was how much percentage lies between minus 2 standard deviations to plus 1 standard deviation. So what percent lies from here to here? Well, all you would have to do is add the sections in between them. So you would do 13.5% plus 34% plus 34%. And that would tell you the percentage between the 2 standard deviations less than and 1 standard deviation greater than. All right, and we're going to apply those here in this next set of problems. But again, this would be an important thing to draw, so you got the percentages in each of those. And if we went through and added all of these, which wouldn't be a bad idea to go ahead and do, we should get 100%. So let's go ahead and, if you wanted to just take a second and double check that, add these all up, make sure I did the math correctly. And we should get approximately 100% there. Sometimes it will be just a little bit off based on rounding, because you got to round all of these, but it should be 100% or close to it. All right, let's go ahead and answer a couple problems. Sorry, my slides are a little bit wacky here. All right, let's just start with this one. The heights of male students is normally distributed with a mean of 170 centimeters and a standard deviation of 8 centimeters. Find the percentage of male students whose height is, and then we're supposed to draw and label a bell curve to help, and we're going to answer some questions here. So we're just going to draw a sketch of one. It is important that you're doing this on your own as well. The mean is 170, so that tells me right down the middle there. It's going to be 170. I'm going to draw this out. And obviously this is not a perfect bell curve in any way. It says the standard deviation is 8. So mu equals 170, sigma equals 8. So what I'm going to do is I'm going to add 3 standard deviations to each side, and I'm going to subtract 3 standard deviations from the left side. So if I were to add 1 standard deviation here, it would be 170 plus 8 would be 178. If I were to add another standard deviation, that'd be 186. And add 1 more standard deviation, that's going to be 194. And then if I were to subtract, going the opposite way, subtract 8, so subtracting 1 standard deviation would give me 162. If I were to subtract again, I would get 154. If I were to subtract again, I would get 146. So these are going to be important mile markers. Again, this is like mu plus sigma. This is mu plus 2 sigma. This is mu plus 3 sigma. This is mu minus sigma, mu minus 2 sigma, and mu minus 3 sigma. So that's where I came up with those. 170 is right in the middle. That's mu. All right, so now we're going to figure out some percentages. So the first one asks, what percent is between 162 and 170? So it's basically saying how much is in this shaded area, right? Well, that little graphic we just made, how much is in that first shaded area? Well, that's 34% because it's half of 68%. So I would say 34%. So 34% of the male students had a height between 162 and 170 centimeters. All right, if we were asked how much is between 170 and 186, some of this. So 170 and 186. My eraser is not working. Okay, never mind. I guess I'll forget the eraser. I'll just do a different color. So between 170 and 186 is going to be from here to here, right? So we want to add this one and this one. So we know this is 34, right? You might want to refer back for the other one. And that one is 13.5. Okay, so you just do 34 plus 13.5. So that gives us approximately 47.5%. Would be between those two. The next one, how much is between 178 and 186? So find 178 is right here, and 186 is here. So it's saying how much is in that section. Well, we just said that that was 13.5%, so that's easy enough, 13.5%. Less than 162 would be from here all the way to the end. So you need to figure out how much is in this section plus this section plus this section. So if we look back, well, we'd have our 13.5. So we're going to do 13.5 plus 2.35 plus 0.15. And that gives us 16. That was 13.5 plus 2.35 plus 0.15. So 16% of the students would be less than 160 centimeters tall. If it was less than 154, well, that's going to eliminate one of them now. Just go from these two over, right? So we would just not include that 13.5. So it would just be 2.35% plus 0.15%. And that would be 2.5%. And then greater than 162, that's going to be everything shaded from, shaded to the right of the 162. So all of this, the easiest way to figure that out rather than adding those all together is we knew everything less than 162 was this one, right? Was 16%. So greater than 162, we know it's all 100%. So we just do 100% or just 1 minus 0.16 or 100% minus 16%. So that gives us 84%. It'll be everything greater than 162. Right. Let's try another one. Again, on all of these, I would draw a normal distribution and label it just like I did. Going to make things much easier on you. So this one says, in a survey, college students asked how much time they spend talking on the phone per day, playing games on their phone per day, texting, and several other activities. According to the results, average college students spend 33.1 minutes per day in conversations on their phone. I think this is kind of outdated because I doubt people your age actually spend 33 minutes on the phone in conversations. I know I do not spend a lot more time texting and other things than talking. So, but maybe you like to talk a lot. All right. Standard deviation is 2.7. So we're going to go ahead and draw our normal curve and try to answer these questions. So don't skip this part of drawing the normal curve. It will make things way easier, I promise. So our mean there is 33.1. Even if you're terrible at drawing, the picture will help you answer the questions. And then I'm going to do one standard deviation here. So I'm going to add, it's 2.7. So I'm going to do 33.1 plus 2.7. I get 35.8. Then I'm going to add it again. So I'm just going to hit plus 2.7, 38.5, plus 2.7 again, and I get 41.2. And then I'm going to go the opposite way. I'm going to subtract. So I'm going to do 33.1 minus 2.7, 30.4, minus 2.7 again, 27.7, minus 2.7 again, and we get 25. So there I've got, again, this is mu plus sigma, mu plus 2 sigma, and mu plus 3 sigma. This is mu minus sigma. You don't have to write this every time, but just want to make sure you know what's happening here. All right, so question is approximately what percent of students talk for more than 38.5 minutes per day? Now notice all of these questions are going to ask you questions about numbers that are written here. You'll never get a question at this point about a number that's not written on here. So this is talking about 38.5. And it says how much is talk for more than 38.5. So all you're going to do is add these two little sections, this one plus this one. So you can even refer back. Well, we've got 2.35 plus 0.15. 2.35 plus 0.15. So that is 2.5%. So a very small amount of students talk more than that. All right. Next one was among the top 16% of cell phone makers. So among the top 16%, well, let's go ahead and look at our chart real quick. If I can get back there. So top 16%. My slideshow is not working. I'll get back to this chart here. So top 16%. Well, I said approximately, and if we look at these three ones put together here, we got 13.5, 2.35, and 0.15. If you add those together, you're actually going to get 16%. So it's going to be everything greater than that one standard deviation of the mean. So let's go back to that one. So everything greater than that would be 35.8. So in order to be in the top 16%, you would need to talk for 38.5 minutes in order to qualify for the top 16% of talkers. So 35.8 minutes. And last question, how much would a respondent have to talk to be in the top 0.15%? So the top 1.5% is this very little part up there. So in order to be in that one, you got to talk for more than 41.2 minutes. So we can ask these questions in reverse as well, right? We can ask about given a value, find a percentage, or we can say given a percentage, what values would fit that model. I think we've got one more to practice this, yeah. All right, this is just a very basic question. Not really applicable, but helps practice it nonetheless. It says if we have a normal distribution, mean of 121, and a standard deviation of 40, I'm going to go ahead and draw that. Again, it does not have to be perfect by any means. Mine never are. Go ahead and put our mean in the middle, 121. So we're going to label 3 standard deviations each way. So I'm going to go 1 here. I'm going to do 121 plus 40. That's going to give me 161. Plus 40 again, that gives you 201. And then plus 40 again, that gives you 241. If we go minus, that's going to give us 81. Minus 40. Minus again, that gives us 41. And minus 40 again, that's going to give us 1. So there is our normal distribution. From there, what interval contains 68% of the values? So remember, 68% lie within 1 standard deviation of the mean. So that's going to be 81 to 161. Okay, what contains 95% of all values? So if we look at our chart, we want 95% of this data. There's actually a couple different ways you could look at this, I suppose. I can get back to my chart. There we go. So 95% of the data. Basically, we want to exclude 5%, right? So how could we exclude 5%? Well, if we look at, I guess we can just use the rule that I gave you earlier, which is 95% is within the 2 standard deviations here. But the other way, how I was going to explain it, is if you want 95%, you need to subtract out 5%, right? So in this one here, there's 0.15, and this one has 0.15, and this one has 2.35, and this one has 2.35. So add those together, you get 2.5%, right? And these two, and add these two, you get 2.5%. Add those together, it makes 5%. So we would want everything left over in the middle. So we would want all of this stuff here would be left over in the middle. That would give us 95%. So that would be between 41 to 201. Or again, you could just use the rule that it's within 2 standard deviations of the mean. So 41 to 201. The interval with 99.7%. Well, that's 3 standard deviations of the mean. Again, you could calculate it the same way, but that's going to be 1 to 241. What percent are above 201? Okay, so that's going to be this part. I'm having the hardest time today. All right. So above 201. I don't know why I can't get this thing figured out. All right, above 201. Every time I click it. All right. Well, it should be 5%. For whatever reason, every time I click it, it's changing. There we go. All right, above, is 5%. Above 201 is going to be 2.35 and our 0.15. So it's 2.5%. And then what percent are below 81? So below 81, it's right here. So we need this section, and this section. So each one, if we go look at our chart, we've got 13.5, we've got 2.35, and 0.15. So we add those together, and that was 16% when we did that earlier. So 16% would be the answer to that last question. Let's do it again. All right. Hopefully you got a good understanding of that. You're going to have a lot of questions related to that on both an assignment and a quizzes. Key takeaway is make sure you're drawing these charts. That makes things way easier if you draw these charts. Sorry if you got a little confused in all the flipping back and forth and technology issues there, but make sure you do reach out to me if you have questions. All right, good luck, guys.